Welcome to Spring LIB.
Okay, so let's draw a free body diagram of the scenario that we have. So we have a slope which has an angle of 65 degrees, and then there's a ball which is sliding down the slope, and it's rolling without slipping. So if we draw a free body diagram, we can choose axis according to our convenience. So let's choose the perpendicular to this slope as our y-axis, and parallel to the slope is as our x-axis. So we can see that mg, or the mass of the ball, will be acting straight downwards. We call it m times g, and the normal force will be acting along the y-axis. So there's our normal force. Then there will be the frictional force, which will be acting opposite to the direction of the motion of the ball. We call it Fs. Then there will be a component of mg along the y-axis and along the x-axis. And along the y-axis, this is going to be mg cosine theta. Let's call this as angle theta. So this is angle theta. And along the x-axis, this is going to be mg sine theta. Right. So that's the free body diagram that we have, and then the ball is rolling. The ball is rolling down the slope with an acceleration a. So if we solve the linear part of the motion, we can, like, for the first part, let's just ignore the slipping. So we'll have the sum of the total forces. Let's call it the external force, and by external force I mean the force due to gravity. So that should be equal to m times a, center of mass. Because it's a linear motion, we just consider the ball as a point object with which is sliding along the slope. So that's why we're just considering the center of mass. So along the y-axis, we have Fy, which is equal to m times Ay. From there, we have N, which is equal to mg cosine theta. So that's the normal force, which is counterbalanced by the cosine component of mg. Then we also have the x direction, where Fs will be equal to so Fs is the coefficient of static friction times the normal force, which is mg cosine theta. So we can write, since the ball is actually rolling down this slope with an acceleration a, so that means mg sine theta minus this force Fs will be equal to m times a. So mg sine theta minus this quantity right here, which is mu s mg cosine theta, should be equal to m times a. And from here, if we get rid of the m's, we get g times sine theta minus mu s cosine theta, which is equal to a. Right. So we have figured out the equations of motions for the linear direction. Now let's think about what happens when the ball is rolling. So let's say this is the ball which is rolling. Now the direction of the torque is going into the page because the ball is rolling this way, and let's call the rotational acceleration as alpha z. So we have the normal force, let's use a different color. We have a normal force acting this way, and then we have the gravitational force acting downwards. Then we have the radius, which is r. So the frictional force is acting along this way. We call it Fs. That means one thing before solving the problem, we see that mg and n, they're acting at the center of the ball, so that's why there's no torque due to these two forces. So the only force that we'll have due to torque is the force due to friction. So that means we write the total torque, which is torque due to friction, should be equal to mu s mg cosine theta times r. Remember that torque is basically force times r, so that's why we already know that we're only dealing with the frictional force, so we just multiplied the frictional force with the radius vector. And for our case, since it's a solid sphere, so I, or the moment of inertia, is 2.5 mr squared, where capital M is the mass, or let's actually write small m just to be consistent. So that's the mass of the solid sphere. Now, using tau z, because it's acting in the z direction, equals ICM alpha z, we can also figure out torque from here, which is this quantity times alpha. So we can actually compare these two to solve for our mu s. Now, what we get here is mu s mg cosine theta times r is equal to 2 over 5 mr squared times alpha z. So from here, we can get rid of the m's, first of all. Then we know that since the sphere is not slipping, so we can say alpha is equal to a over r. So we can substitute that as well. And if we do so, first of all, we get mu s g cosine theta equals 2 over 5 alpha. Now we can use the relation that alpha is equal to a over r, and get a as 5 over 7 g sine theta. And the way we get that is we substitute alpha here, so we get mu s g cosine theta r, which is equal to 2 over 5 a. So we have one equation over here, and then we have another equation over here. So if we solve for these two equations, we get alpha, and of course we can solve for mu s as well, because we have two unknowns and two equations. So mu s will be 2 over 7 tan theta, which is equal to 2 over 7 tan 65 degrees, which is 0.613. So that's the coefficient of friction when the ball is a solid sphere. Now, if we have a hollow sphere, the only thing that will change is the moment of inertia. So now the moment of inertia will be 2 over 3 times mr squared. And then our a, or the acceleration, will be 3 over 5 g sine theta, and mu s, or the coefficient of static friction will be 2 over 5 tan theta, where theta is 65 degrees. So mu s will be 0.858. So we can see that the value that we got here is not large enough um, to prevent slipping for the hollow ball. So for hollow ball, we need a friction coefficient of static friction of 0.8, which is definitely larger than what we calculated for the solid sphere. So this is not, so that means mu s calculated in part A is not large enough to prevent the hollow ball to slip. Now in part C, we just have to explain why we're using the static friction coefficient. So the only reason for that is the ball is not slipping. So ball is not slipping. Since the ball is not slipping, that's why we can say alpha is a over r, and that's why we take the static friction. If the ball was starting to slip, then we would have taken the coefficient of kinetic friction. Thank you.